Hi everyone, thanks for joining. My name is Nitish. In this session, we are going to talk about CI challenges with large monorepos. Before we start getting into the topic itself, I'll briefly introduce myself. My name is Nitish. I work as a staff engineer at Oscar Health. I work for a team called Developer Productivity. I have 4+ years of experience with Monorepo and CI in general. Prior to joining Oscar, I was working for a startup, and before that, I was working for Bloomberg. I think it's equally important to understand what is Oscar and how big is Oscar Monorepo. So, what is Oscar? Oscar is a full stack health insurance company, meaning it is trying to build all the core modules to run a health insurance operations in house, that too on modern tech stack, like, for example, AWS, Python, Golang, JavaScript, and so on. We are currently serving over 1 million plus members across 22 different states and 607 counties. And we have around 70% CAGR over 4 years in our membership base, and around 60% CAGR over 6 years, where CAGR stands for cumulative aggregate growth rate. This sort of grand vision to build a full stack health insurance company is leading towards a lot of microservices that we have built in house. So let's see Oscar Monorepo in numbers. We have around 100,000 files in our Monorepo, which has around 19 million lines of code, out of which 5 million lines of Python and SQL each, then around 770K lines of Golang, and then around 2 million lines of JavaScript. Another lens on the Monorepo could be from microservice point of view. Then from that point, we have around 2.3K binary targets, aka microservices. We have around 12K libraries and then 6,000 tests. From CI/CD point of view, Oscar engineers deploy around 5,000 binaries per month. Then we run around 4 million tests per month, and then we collect around 15 TB of artifacts per month. These artifacts could be logs, binaries, Docker images, etc. Now, when this monorepo kept on growing linearly over time for us, we started running into a few interesting challenges. The first challenge was running the entire test suite on every div was not an option for us anymore. So we had to go back in and figure out how to trigger only the change targets on a particular div. The second interesting challenge we started running into is basically Git cloning the entire monorepo and fetching all the related third parties from scratch on remote CI servers was becoming slower and slower over time. So we had to figure out some caching techniques to make sure these two large objects are being accessed on remote CI server in somewhat constant time rather than a linear time. So in this session, we are going to see what solutions Oscar has put in place for these two problems. So let's start with the first one, which is calculating change targets on a diff. In plain English, is really straightforward how Oscar does it. The first step is we first find all the change files in a diff. Once we have that, we find all the transitively dependent test and binary targets from the change files, and then we go test them. Second bullet point seem fairly easy in plain English, but it can get fairly complex. And I think for us, it's decently complex, and we'll see how. Uh, Before we actually start getting into more details about this, let's just make sure we understand what it means to calculate change targets and to find all the transitively dependent targets and so on. Let's assume a simple monorepo which has 4 targets A, B, C, D, where A depends on B, B depends on C, and D depends on C. Now let's take 3 different scenarios. In first scenario, let's say someone changes file C. In that case, we are going to have to test A, B, C, D, all 4, because A depends on C through P as well. Then let's say somebody changes file B, then we need to test target A and B only. We can omit C and D in this case. And let's say somebody changes file A, then we only need to test target A. So in the last case, as you can see, we didn't even test 75% of the target. Actually, in practice, this gets even more optimal. In our case, every build, every diff can potentially have 10,000 targets that we need to test on that. Essentially, that's the entire monorepo. But on average, we are only testing 400 targets on every diff. That means we are not testing 96% of the targets because of this strategy. So adding this module is extremely important in large monorepos, and assuming we have a decent understanding of how to do it as well now. So now, assuming we have decent understanding how to do it and also the importance of it, now let's start getting into how Oscar does it. So luckily for us, Oscar was using this build system called PANTS, which pushes Oscar engineer to formally define all the targets into build files, and these build files are checked into our monorepo itself. So this is a target definition for one of the Python binaries, where you can see a name, source, and all the other Python library dependencies for that Python binary and so on. So once we have all these target definitions stored into build files, and these build files are checked into a data repo, and all these collective build files are 440K lines total. Uh, when we combine all these build files lead to a giant build graph. And on this build graph, we are able to run some interesting queries. One of those interesting queries is basically finding all the change targets. And one of the that you are able to see that simple query here. At this point, you are able to guess that actually running the graph query is fairly straightforward. But where the majority of the work lies is maintaining that build graph in the first place, aka maintaining all those build files. So for that, my team is responsible for implementation of Pants at Oscar. So my team has provided tools to ensure we have ways to update these build files in automated manner, and we also ensure we have ways and processes in place to make sure these build files are in valid state and so on. So now once we have a list of change targets, we start feeding them onto our auto scaling remote CI servers, and those remote CI servers use some interesting caching techniques in place to be able to give results back to the user in timely manner. Right. So let's in the next section we are going to talk about some of those caching techniques on remote CI servers. So before we start talking about caching, let's look into what are the objects we need to cache in the first place. So there are two objects which kept on growing linearly over time for us. One of them is Monorepo itself, and the second one is the third parties which are defined in the Monorepo. So we are going to see some techniques to actually be able to cache these two large objects to be able to access on remote CI server in constant time. So techniques for caching usually differs from what kind of server type it is. For long-running servers, they're usually fairly straightforward to cache, and things can get slightly difficult on ad hoc servers. So let's see both cases one by one. So let's get the simple stuff out of the way, which are long-running servers. In long-running servers, things are simple. We first clone the repo once the server comes up, and then after that, throughout the day, we keep using git commands to fetch new changes. And to sync third parties, we just sync them whenever needed, and we just keep them on long running server as it is. So yeah, as I said, fairly straightforward. Things can get slightly interesting with ad hoc server. Ad hoc server are not completely unavoidable because they are usually auto scaling in nature, and basically the cluster which is responsible for executing our test jobs, they can go up to 160 machines during the peak load time, and they can go down up to 20 machines during the weekend. Right. So when we are launching these ad hoc servers on fly during the daytime, we need to make sure they are able to join the workforce in a timely manner, and so that's why we need some sort of caching techniques in place. And we're going to talk about how. So first thing we do for caching on ad hoc server is we build a Docker image at 2 a.m. every night. We call it nightly Docker image. In this nightly Docker image, we pack three things. First thing, the base packages. These base packages is OS itself, which is required by the Monorepo. Then some base packages required by the Monorepo, like MySQL, Postgres, and so on. And once we have the base packages, then we git clone the Monorepo itself, which is 6 GB. Once we have the Monorepo git cloned, then we go inside the Monorepo and we run some pants command to fetch all the third parties as well. Once we have the third parties as well, we commit that container, and that container becomes a nightly Docker image. And this nightly Docker image is 14 GB in size. Once we have this nightly Docker image built out, second step we do is we go cache it. For caching, we do two things. First thing, we go cache it on all the ad hoc servers which are currently up and running. That's the first thing. Second thing we do is basically we make sure we have a mechanism in place so that when a new ad hoc server is up and coming, it is able to download this 14 GB Docker image directly from S3 rather than doing it from Docker registry. Because let's say if we are launching 100 servers at the same time and they start Docker pull at the same time from Docker registry, our Docker registry was getting overloaded. So that's why we had to create that extra mechanism. So now once the caching of this nightly image is done, problem becomes slightly easier. Now let's imagine somebody creates a pull request or a diff. then what we do is we go on the ad hoc server, we open a container for that nightly Docker image. In that container of that nightly Docker image, we patch that particular diff, and we also patch all the third parties which may have been introduced in that pull request, and then we commit that container back. So now this extra layer, which is sitting on top of the nightly Docker image, which essentially is the pull request itself that the user created, is very small, is 10 MB in size, and that's the last layer. And essentially now to create that pull request environment in any of the ad hoc server is going to have to download only 10 MB of the layer size, because nightly Docker image exists on all of those ad hoc servers. And this 10 MB is the magic and because of that, we are able to create a constant time execution for our remote CI servers. Just to give you some numbers on this, let's say before this whole system was in place, it used to take around 5 to 10 minutes to build a particular binary. But after we put this system in place, it usually takes around 1 minute to build a binary. And this 1 minute has been constant for us over time from last 4 or 5 years. But in the other case, the build times were constantly increasing linearly as the Monorepo kept on growing. Yeah, so, and this has been in production for 5 years, if I already mentioned, and this is working pretty nicely for us. And this last slide is our system diagram for our CA system. As you can see, it has been growing complex over time. And the reason for its complexity is basically ensuring a large monorepo and its all of its target is always buildable state at all times is not an easy problem. But I find this problem extremely fascinating. And if you have any more further questions on Monorepo, CI, or even distributed systems in general, feel free to get in touch. This is my email and this is my Twitter handle. And thanks for paying attention. Thank you. Bye-bye.